Lesson 12.6. It's time to do more difficult logarithms. So at this point, you have done the basics of solving logarithms. You've realized that there are really only two options. That has not changed. Your goal is either to be able to drop the logarithms because you have a log on each side, so then you don't need it anymore. That's option one. Or option two, you condense each side, ideally this one side, and you would have, the logarithm, um, yeah, that you could then, once you have one logarithm, loop swoop, 2 to the third equals what? So then 2 to the third, that's a 3. 2 to the third is 8. So those are your two options. Now, it's going to get a little more complicated than that because we have to do some condensing and get a little creative sometimes. But for the most part, it's not too terrible. And it really does boil down to one of those two options. Okay, so one thing before we get started. It is possible for you to have extraneous solutions. Now, we did extraneous solutions a lot of times throughout the course of the year. Most recently, we did extraneous solutions with solving rationals. So, just in our last unit, Unit 11. So, for solving more difficult logarithms, I need you to know that you're going to have to check your answers. And that can get frustrating because you've already spent a lot of time solving your questions, solving your equations. Now, it's always important for you to know why you get extraneous solutions. Remember that a logarithm looks like this. It has a vertical asymptote that is like really thick. It has a vertical asymptote along the y-axis. And also notice that there is nothing over to the left. You don't go past that vertical asymptote. So your base, whether it's a growth greater than 1 or a decay in between 0 and 1, the parent will never go to the left, to the negatives. So what I'm trying to tell you is you have two things that are going to be an issue. One, you can't take the logarithm of 0. Why? Because there's an asymptote. Two, you can't take the logarithm of a negative number. Why? Because there's no graph over there. It doesn't exist. Now the question is, why doesn't it exist? So, your first option, why can you not take the logarithm of 0? Let's say we picked any base. Let's just keep it common. Let's keep the common logarithm of base 10. So if I asked you to evaluate this, if I said, okay, what is log base 10 of 0? What you need to recognize is that that doesn't exist. It's not going to happen. So why doesn't it exist? Well, think this through. 10 to the what equals 0. Someone's going to think, oh, the exponent is 0, the answer is 1. Okay. If the exponent is 0, isn't the answer 1? You just said it. It's not going to happen. So then someone says, well, what if it's 1? Okay. What is 10 to the first? Is 10 to the first 0? No, 10 to the first is 10. Again, that doesn't equal 0. Someone might say, okay, what about negative 1? All right, that's 1 over 10. In any of these options, are we ever going to get a 0? No, we're not. It's not going to happen. So you can't take the log of 0. It literally doesn't exist. Can't do it. Now, the other option, you cannot take a log of a negative number. So, and that's any negative number right there. So if you had something like, we'll keep it with log 10. Log base 10 of negative 100. This is a common misconception. So log base 10 of negative 100. Why can't you evaluate that? It doesn't seem like to be that big of a deal. Someone's going to say, oh, well, that's easy. 10 to the what equals negative 100. 10 to the what equals negative 100. Someone is bound to say, oh, it's -2. Mm-mm. A negative exponent sends it across the line and changes the sign. That doesn't make a -100. Oh, and actually that would be squared. So it's 1 over 100, not -100. That's not correct. That's not equivalent, clearly. Someone might say -1. That's going to be 1/10, not 100. Not -100, excuse me. Someone might say 0. And with the exponent of 0, the answer is 1. All of these things, none of them are going to get you anywhere to -100. It's not possible. So, moral of the story. Let's make this so it's easy to read. Okay. If you find yourself taking the log of 0, whatever your base is, doesn't matter. But if you find yourself taking the log of 0, in this case, base 10 of 0, it's not possible. You have to understand that what you've got as your answer will not work. So whatever your answer is, if it makes whatever you're taking the logarithm of 0, if it makes this happen right here, it's extraneous. It's not going to exist. Now, if you take the log, no matter what the base is, of a negative number, we have this same problem. That can't be done. So whatever value you think you got to make that happen, it must be extraneous. Why? Because logs of negative numbers don't exist. So let's go to an actual problem, keeping that in mind. Okay, I'm actually really frustrated that this is the one I chose to go first, because it's a doozy. It's a big one. Now, getting started isn't the problem. It's finishing it that's going to be the tough part. Remember that the goal is one of two options. Either you have logs on both sides that you get to drop the logarithms, or you have one log that you can loop swoop to change it to exponential and actually solve it. So your first goal should be get logs together. Now, that's the easy part. This becomes log base 3 of, remember, whenever you're adding, you condense back through multiplication. And when you multiply the variables, you add the exponents. That's base 3. So, easy. We have the same log on both sides. We drop the logarithms. So then the real question is, how do you solve y to the 5th equals 16y? Well, I know, yay, it's exciting. You've got a couple options. Well, for starters, if you're going to factor, because you find yourself with y to the 5th and y, you would have to get everything together on one side. You would then factor out the GCF, which is 1y. That leaves you with y to the 4th minus 16. That is a perfect square minus a perfect square. That is the difference of squares, my favorite. So I'm going to just put this up here off to the side. We've got y. We have y to the 4th minus 16. So if you take your y to the 4th and your 16, a perfect square minus perfect square. Well, the square root of y to the 4th would be y squared. The square root of 16 is 4. And remember, 1 gets a plus and 1 gets a minus. This one can't go any further because that's a perfect square plus perfect square, and you can never factor those. But this one is yet another difference of squares. Y squared plus 4, okay? So then this becomes y plus 2, y minus 2. Finishing this is a piece of cake, except for when it comes to this one, which is not too terrible. It's just you're not going to like it because it's going to give you an imaginary. Let's see what I mean. If you set each of these equal to 0, there's one of them. There's another. third. Remember what we learned about polynomials? Biggest exponent is how many you're looking for. We've got 3 out of 5. So where are the other 2 coming from? Well, if you set y squared plus 4 equal to 0, and you subtract the 4, when you force the square root, you have to show plus or minus. That's always going to happen. And what is the square root of negative 4? 2i. It's imaginary. Did we get 5 solutions? Yes, we did. 2 of them aren't real. They're imaginary. But 3 of them are real. Now here's the last part of this. This is the part that's going to stink. Oh, here we go. There's no point in checking the imaginary, right? The imaginary is a non-issue. It's not on the coordinate plane anyway. But you still have to check the 0 and the plus or minus 2. When you do that, and you plug in to all of these y's, do you see that it only takes 1 to cause a problem? And right off the bat, we have 0 squared, which is 0. Can you take the log of 0? We just talked about it. The answer is no. So 0, it makes it extraneous. Now, let's check negative 2. When I plug in negative 2 right here for y squared, it makes positive 4. So far, we don't have an issue. But as soon as I plug it in here, and of course also here, but it only takes one of them to be a problem, that becomes negative 2 to the third. That is taking the log base 3 of negative 8. Can you take the log of a negative number? You cannot. So that one is also extraneous. We plug in the 2, and the 2 finally works. So we do have a winner with the positive 2. Let's check it really quick. If I put the 2 in for all those y's, I have log base 3 of 2 squared is 4. I have log base 3 of 2 cubed is 8. And that is supposed to equal log base 3 of 16 times 2 is 32. When you condense these, you condense through multiplication because you have a plus sign, and that means you're going to multiply whenever you put them back together. So that would be 8 times 4 is 32. Is log base 3 of 32 equal to the right side log base 3 of 32? Yes, it is. So positive 2 works. Everything else, not worth your time. But you didn't know that until you actually grappled with it and did all the math to get there. I get that it's tough. Not impossible, but tough.